Calculus is one of the most diverse mathematical groups, and is able to be used in just as many ways. It's used in simple things like odometers and flashlights, but also more complicated things like determining planetary alignment and radar. Calculus is not something that's used every day by everyday people due to the complicatedness of it, but most engineers, whatever field that they're in, use it fairly frequently. Here are 4 calculus applications to use in an engineer's life. 1. Electrical engineering and Taylor polynomials. Electrical engineering is familiar to at least some people. Probably, you think of the electrician who helps you wire your house. However, electrical engineers aren't always in the service industry. They've helped invent computers, cell phones, microchips, and solar panels. Quite a resume. The people who fix your computer, they're probably either electrical engineers or computer science engineers. The term electrical engineering was introduced by Thomas Edison to the Columbia president Frederick A. P. Barnard in 1882. The course started as a 2-year course of graduate study offered to those who had already completed the standard 4-year Mines curriculum. There was a grand total of 2 people who taught the program, men named Francis Bacon Crocker and Michael Dvorsky Pupin. Crocker had a background in industry while Pupin was a physicist. It wasn't really until the First World War that electrical engineering really kicked off, as in more than 30 people in a program. So Taylor polynomials, as shown here, can get a little bit extensive. There's a reason why most things are done by computer now. But Taylor polynomials, in this instance, are meant to make sure that the vibration of the wires doesn't interfere with something else, such as another wire. This is vital because if the wires are too close, they can knock into each other and scramble the data being received or retrieved. These equations tell precisely how far apart the wires need to be, though it would be a tiny fraction of an inch. 2. Civil engineering and area under a curve. I am forever being asked, what exactly does a civil engineer do? No, I am not going to be engineering civility between countries, as fun as that may sound. The roadwork construction down the road that's fixing the bridge, a civil engineer is heading that. The pipework being done on the other side of town, a civil engineer is heading that too. A new bridge being built, or an old one being tested for being structurally sound, civil engineer. There's a subcategory of civil engineering called architectural engineering that oversees houses and buildings being built. Long and short of it, you have something that needs cement and or steel to be built, some kind of civil engineer is going to take the project. Civil engineering, by itself, has been around for centuries. From the pyramids of Giza to the Sydney Opera House in Australia, the people behind them, regardless of whether or not they were actually labeled as such, were civil engineers. For a long time, the term engineer could just as easily be substituted with architect, up until the 1700s. In 1747, the National School of Bridges and Highways, France, was opened, and has set the trend for civil engineers pretty much ever since. However, though the term was coined in 1771, being a civil engineer was not actually considered a profession until 1828. You might not think that area under a curve would be relevant to civil engineering, but it is. Have you ever seen a house on a hill? Perhaps one in a basement? Why isn't the inside of the house curved like the hill, or sloping downwards with gravity? It's because they level it with concrete, or dig out enough dirt to account for the basement. How do they know when to stop digging? How do they know when to stop filling? Or better yet, how much concrete do they need to bring in? Most people think to find volume finding calculus, but the disk or shell methods wouldn't work with an asymmetrical and angular object like a house. Those methods rotate around an axis, and finding a round house is just not likely. No, civil engineers draw a line that matches the curve of the hill, and then find the area for what's needed for one side of the house to become level, then repeat it for the rest of the sides and find the volume. 3. Materials engineering and sequences and series. I can just see your thoughts. Materials engineering? What's that? Well, let me tell you. Materials engineers are the people who bring you plastic, carbon steel, ceramics, and semiconductors. Your mechanical pencil? If the plastic breaks for no apparent reason, it's because the material engineer in charge didn't find the impurities in the plastic. Skyscrapers? They're the ones responsible if the steel isn't pure enough to withstand and bend with the high winds instead of simply breaking under the strain. The science behind materials engineering has been around since the Stone Age, quite literally. However, the more modern aspect of this engineering got started with the metallurgy that began with mining. Up until recently, materials engineering was heavily involved with most aspects of chemistry and thermodynamics, as well as how the two influenced specific materials. This was because we were looking at it more for tools and protections from things of Earth. Now, though, most of the recent materials science has developed is because of our urge to explore space, metallic alloys, silica, and carbon materials. The materials engineers pick out impurities, at least with metal, with something called the Anderson impurities model, which is shown by this ridiculously long equation. It uses series to ferret out the magnetic impurities in a metallic host. Of course, this is usually done by a machine where the metal passes through it to determine the impurities, not by hand. Aren't you grateful? 4. Aerospace engineering and parametric equations. Well, that was a mouthful, wasn't it? This is another I know this but I don't field of engineering for the majority of the populace. Aerospace engineers are the people who design, develop, and test aircraft, spacecraft, and missiles. A field that makes you glad that these people aren't actively out to get you. These people use highly advanced math every day to help them calculate velocity, acceleration, friction, and a host of other things to aid them in their various creations. Understandably, aerospace engineering is the youngest aspect of engineering that we've covered. The desire for flight has been oft-repeated dream of mankind and wasn't truly successful until the Montgolfier brothers in 1783. No, not the Wright brothers. The Montgolfier brothers discovered the hot air balloon, and over a century later, the Wright brothers built the first plane in 1903. Since then, the majority of the advances of technology in this field has been due to military demand. However, the first rocket was launched on March 16, 1926, though it wasn't until 1957 that we managed to send the Russian spacecraft Sputnik into outer space. If you think about it for more than 30 seconds, you can probably see how parametric equations can be applied to aerospace engineering. Parametric equations calculate how something goes over the course of a period of time, and can allow you to calculate where something will be at any given point. They are used in guiding missiles, as well as guiding rockets through the atmosphere. This is why rocket launches are done at dusk or dawn. The wind is generally the most still during those times, so the engineer's equations can be as accurate as possible. This photo is a time-lapse of a rocket blasting off, and I guarantee that the arc shown here is almost exactly like the equations that the scientists predicted. Well, there you have it. 4 practical applications of calculus in real-world jobs in the realm of science, technology, engineering, and math. We've covered what electrical engineering, civil engineering, materials engineering, and aerospace engineering are at their cores, as well as a small aspect of calculus that goes into each. We've covered a few examples of the calculus that might be used in those situations. We've covered the beginnings of each aspect of engineering, and uncovered a few surprises of how ancient some of the categories truly are. I hope that you have learned of new types of engineering, some of the math behind your possible future job, or maybe some history that your major was involved in that you didn't realize before. I know that I didn't know the majority of this before I researched it, and I hope that I was able to pass some of it along. Thank you for watching. I hope you liked it. Have a great day.